Hey there, everyone. Welcome back. All right, we're going to start chapter 10 off with some rotational kinematics. All right, so let's hop right into it. What you see here is a picture of a centrifuge. And if you're not familiar with what that is, well, these are vials, right? Or little containers that the medical personnel put various compounds in, right? And so they hang on these support structures here, and then they put a lid on this entire structure here, and then this central rotor spins, right? But it spins such that these vials are free to rotate in those holders, and so the faster this silver rotor spins, these vials will start to you know swing upwards, right? And so this spins very, very quickly around and around and around, right? So the faster they spin, the more these vials kind of go upwards towards horizontal, and that acts to help to separate the different types of materials in the vials, right? The more dense materials will be not attracted, but will, I don't want to say gravitate either. They will move towards the outside of the vial, and the less dense will stay towards the inside. Okay, so the basic gist of a centrifuge is that this silver apparatus here rotates, right? It spins very, very quickly. Okay, so with that in mind, let's answer these three parts here. So the angular speed of a rotor, so this silver contraption, in a centrifuge increases from 420 radians per second to 1420 radians per second in 5 seconds. So, part A here, through what angle does the rotor move in this time? Right? So what's the angle? What's the total angular distance, in other words? Okay. Well, let's see. We have both an initial and a final angular speed, right? And remember that angular speed in chapter 10 now is written as, let's see, where do I do that? Let's do it down here. Angular speed is written as omega. Again, this is not a W, it's the Greek letter omega. So let me put this here. Omega. Okay. This is this is one of the few times I get to really be nitpicky, right? It's not a W, it's an omega. So this stands for an angular velocity or an angular speed, right? I guess it's speed if it's non-vectored, and it's an angular velocity if there's a vector bar. Okay, so the initial one is 420 radians, which is an angle, right, per second, and the final omega is, we'll just write it as omega, is 1420 radians per second. Okay. I guess I'll write it there. Okay, so we want to find the overall angular distance. So in this chapter, remember, we have kind of these angular symbols or angular variables are analogous to what we saw in the 1D kinematics with constant acceleration from chapter 2 and even chapter 4, right? So let me write that off to the side. The chapter 10 analog for position is now theta. The chapter 10 analog for speed or velocity is now omega. And the chapter 10 analog for linear acceleration, A, is now alpha for angular acceleration. So knowing that, we want to find the total angle that this centrifuge spins in 5 seconds. So we don't yet know the value for the angular acceleration, right? We know a time. We know both initial and final angular speeds. So if you think back to chapter 2, which of those major equations, that there were 4 or 5 major kinematic equations that we used? If you look back, you should see this equation. right? Or rather, the form of this equation. Whereas back in chapter 2, this would have been 1/2 times the sum of v naught plus v times t, right? But now in chapter 10, it's not v, it's omega, okay? So we know everything in here, so let's use this equation. Let's see. 1/2 times 420 plus 1420 times 5. This should give us, if I did my calculations correctly, this should give us 4,600 radians. Okay, and again, omega is in units of radians per second, not degrees per second, right? And that's very important, all right? The SI unit for an angle is a radian because it's basically unitless, right? Or, sorry, it's dimensionless. So that gives us an angle of 4,600 radians. If you want to convert that to degrees, you can. And really, that's what we're doing in part B here. So we want to find how many total revolutions is 4,600 radians, right? So one revolution means one complete rotation, one complete cycle, one time around, in other words. So let's take 4,600 radians, and we want to basically put it in units of degrees. So we need to convert. We need some conversion factor here, right? Cancel out radians. So we know the factor of 2 pi radians to 360 degrees. And 360 is one complete rotation, or in other words, one revolution. So let's do that. So 2 pi on the bottom. So radians cancel out. And then 360 degrees on top, which will leave us in units of degrees. Actually, tell you what, I don't actually have that number down, but we can do that as kind of a shortcut, right? One revolution is the same thing as 360 degrees, so let's just do that. And this number I did calculate. So that gives us 732.1 revolutions, right? If you wanted to find out how many degrees, you could just multiply by 360. But that's a lot, right? 732 times around. This guy goes 732 times around in 5 seconds. That's incredibly quick. It's incredibly fast, right? So thus, the angular acceleration would need to be pretty large, right? Even if you think of it, 420 radians per second, like that's pretty quick as well. So part C, we're finding alpha. We're finding alpha. Let's see. One of the kinematic equations was this one. We had the angle equals, or the final angle equals the initial angle plus omega naught t plus 1/2 alpha t squared, right? If we're just starting from some time, then really the initial angle here, we can just say it starts at 0, right? This would be what we calculated up here. We have a time. We have an initial omega. So we could use this to solve for alpha, right? That's a little bit more complicated than what we might need. Let's use this equation here. Let's use simply the definition of what alpha is. There. So the angular acceleration, just like in chapter 2, was defined as a change in speed, in this case an angular speed, divided by a change in time. And in this case, I've set the initial time to 0, right? Such that that t is just denoting the final time of 5 seconds. So we have 1420 radians per second minus 420 over 5, right? So that's, what, 1,000 over 5? Yeah, which is 200. The units, of course, are, let's see, radians per second squared. So that centrifuge spins up very quickly, okay? So, again, here in Chapter 10, we use the exact same formulas, right? The form of the kinematic equations are the exact same as what you used in Chapters 2 and 4, right? However, now we're simply using theta, omega, and alpha instead of the linear versions, okay? So with that, thanks for watching.